Okay, let's make a start. So today's lesson is going to cover one of the newest topics in the math method study design, algorithms and pseudocode. In the Unit 1 and 2 book, there are a whole 3 chapter sections that cover it, and this is the only place that it's actually covered. Even in the Unit 3-4 book, they actually don't even have any sections on this. That's not because it doesn't appear on the final exam, because it does, mostly in the multi-choice section, and I think they kind of do like one question in the multi and one question in the extended response section for the actual final exam. But for whatever reason, they don't actually have any of this stuff in the Unit 3-4 book. So just as a heads up, when you do go into Unit 3-4, you don't really want to be forgetting these things, but you'll have to sort of be practicing them in the Unit 1 and 2 book when you get it. As I said, it's a relatively new type of topic. It's going to be relatively math light. We're not going to be doing a whole lot of actual math in here. This is a discussion as to essentially how you can think of functions, relations, or just overall processes that you do in math into essentially step-by-step instructions. How you go from starting to finishing effectively. Like for instance here, what you're seeing is a flowchart of how you would describe this piecewise function, right? Piecewise function meaning, of course, you have two separate rules or functions that are valid for different values of x. So for all x that's greater than 0, you would have the x plus 3. For all x that is less than or equal to 0, you would have this linear instead. That's what this is going to be covering. There's going to be like relatively 1 or 2 questions that this will show up for in the exam, but they are guaranteed to show up in the exam. So if you can get these sort of concepts right, then that'll be 2 to 3, maybe even 4 marks worth of free marks, essentially. So let's have a look. First things first, we discuss this idea of variables. So variables in math work much the same as variables in algorithms and pseudocoding. They are there to essentially represent what could be a value. The slight nuance that you have on it in algorithms and pseudocode is that variables are always assigned a specific value, whereas in math, in methods, they are always unknown unless you're specifically solving for a type of condition. The way you notate assigning a variable is with this arrow. So this would say that a gets the value of a plus 5. Or in other words, whatever a used to be, add 5 to it, and then replace the new a with that value. So if a beforehand was 3, then a gets a plus 5 would mean that a is now 8 in that circumstance. So for instance, if you're keeping track of what's happening over time, step 1, a would be assigned 3 in this example. Then the next line of code would be run, and you would be adding 4 to the value that you just have and replacing it. So the new a is now going to be 7. Then when you do a gets a minus 1, you're not using this one anymore, you're using this one. So when you're working with these sorts of things, it's common to maybe not go like a full table like this, but at least some way to keep track of what's happening from step to step. Addition, subtraction, multiplication, all these things work the exact same way. The only thing that's a bit different here is going to be this arrow operator. You can think of that as just a replacement for the equal sign. It's like a replacement operator. This is replaced with that. This is replaced with that. Any questions as to how that's working so far? Another thing they start to discuss in this chapter section is flowcharts. We would have seen some kind of flowchart before, but maybe not with the specific nuances of how methods wants to describe things. You'll notice there's different shapes and different colors. The only thing that really matters is the shape and the what goes in those boxes. So every flowchart is going to start with a start, end with an end. That is entirely black, but it's supposed to say end there. Dear God, do they really make them all black? Ridiculous. It's supposed to stay. It's supposed to say end. you'll have these parallelogram type things. Those are inputs to your program or your flowchart. Inputs are pretty much always going to be the variables of your thing. So in this case, nothing's actually told to us about what's happening at the start of this algorithm. And so we need to essentially prompt a spot in there to actually receive the value that we're going to be using. So because X is one of our inputs, we want to make sure we're grabbing a copy of X before we do anything with it. Then to describe this split between X being greater than 0 or X being less than or equal to 0, we use a decision diamond. And it just simply says there, is X greater than 0 or not? You've got a yes branch and you've got a no branch. It works exactly as you might think, right? If X was greater than 0, you would go down this path. If it was not, you would go down this path. And you'll notice that those are written in rectangles, and those rectangles contain the rules for each of those possibilities. Right? If X was greater than 0, then you would have gone down this path, and sure enough, that's the one that contains X plus 3. Or more specifically, Y is being assigned the value X plus 3. So if X here was initially 3, X is greater than 0, yes. 3 plus 3 is 6. Y is going to be 6 in that case. Versus if you had some negative number or some 0, you would be going down this route instead. Both of those can then converge onto a print operator. So this is also going to be in a type of parallelogram shape. You typically use those for anything where the output, what do you use those for? You use those for anything where you are either taking in something from outside of your code or your flowchart, and you are taking something from inside to outside. So basically the flowchart is describing this, and you use these kinds of parallelograms when you're taking things into that program and out of that program. Input X came from outside of this. Y was generated in this, but we're putting it to the outside of the flowchart. This is very common in programming languages. Print would print directly to your console or wherever your program prints text to. And then we end it with an end. Both of those have the same shape as the start and the end, just there to basically cap off your flowcharts there. That's a fairly standard basic algorithm there. We're taking in some X value, we're making a decision based on what it is, doing some processing on it, and then printing it out at the end. That's the gist of what's going on there. Is there anything in there that's needing more clarification? I know it's very different to what methods usually is, but something you do need to know, unfortunately. Cool, okay. What do I got going on here? So this is just going to run through some complications that come up. Before I do though, one thing to highlight with this particular area of study, a lot of the time you won't be creating your own algorithms, like you won't be writing an entire flowchart or anything like that. It'll be about you either pointing out a mistake that's in there, or it'll be you substituting in an additional step in there. Like let's say, for instance, you were given this as your flowchart, and one of these boxes might have been removed. You'll be told some background information about what it's supposed to do, and then you'll be told, hey, fill in that blank. That's one possible question that will come up in the actual exam. The other one might be, hey, here's what this is supposed to do. Here's the algorithm that you're given. What's wrong with it? Why doesn't it work? That's what this is supposed to be teaching here, this next example that we'll have a look at. So I paused there to mention that just because this there's a lot going on in this new area of study. I don't want you to think you have to write out full algorithms and pseudocode yourself. A lot of the time you'll be given a lot of the framework and you just have to fill in literally one spot in it or detail what would be wrong with it. That's the gist of it. Anyway, so this algorithm is intended to swap two variables. So you've got this A variable, you've got this B variable. We're just trying to swap the positions of those variables. These are the steps they've outlined. So they're taking input for A and B from some external source. A is going to get the value of B is going to get the value of A, and then we print A and B. One of the issues, actually before I say anything, does anyone spot an issue with what might be happening here? It is written on the page, but I'm curious if anyone sees anything what's wrong with how this doesn't do what it says it does. Seeing you come off mute, but I can't actually hear anything come through.
Okay. Am I audible?
Yeah, that's a bit better now.
Okay. So, yeah, they're not solving the value. They are instead having like a circular reference.
Yeah, could you explain that a bit more? Maybe with like an example. So let's say we have like A is 1 and B is 2. What's going on there?
So if A is 1 and B is 2, if we assign the value of B to A is now 2 and B is 2. So instead of, and in the next step, it's the value of A is put into B, but A is 2 now. So B is still 2 instead of 1.
That's it. Yeah. So this step here has overwritten what A used to be. So when you go and put A back into B, well, it's been overwritten by, in our example, it was going to be 2. So then when you print A and B, you're going to have 2 of the same number rather than 2 of different numbers. So yeah, that's just a very classic case of things happen in sequence, and the things that happen in previous steps will impact the things that happen in later steps. So what they're proposing here, and it's a very common thing to do this in actual program writing, is a temporary variable. So this doesn't actually see any use outside of the algorithm. It's purely there to store something so that we can properly swap the variables. So we're still going to start it off the same way with an input of A and B, but we knew previously, okay, if I just try to swap A and B with the two A and B variables, I'm going to run into a problem. So what I'm going to do is use this third variable as a little buffer, a temporary spot. I'm going to take my A, let's say it was 1, and that's going to be stored into temp. So now temp is 1 and A is 1. Then A is going to get the value of B, which in our example we made it up as 2. Actually, we should probably use the ones they've got here. So they've got A being 2, B being 3. So that was step 1, grab this. Step 2 was temp getting the value of A, so that's this here. 2 is now in both A and in temp. A gets the value of B. B was 3, so now A should be 3. And then B gets the value of temp. We stored what the value of value of A was beforehand, and so now we can actually reuse that because temp did not get overwritten. Just a minor thing that'll come up. So for instance, you might be given this set of steps and you'll be asked to figure out what's going on. The answer would be it's being overwritten. If you had to propose a solution, you might propose a solution of using a temporary variable. One basic sequence that might be asked in the exam. Clear enough how using a temporary variable can help in this circumstance? Nice. The book calls these things desk checks, where you just sort of write up all the possible variables, and each step of your algorithm, you write out what those values are at any given time, which is nice. It's a little bit heavyweight for a lot of things because a lot of the time you're only ever really tracking like one thing that actually matters. One of these variables is the most important one. In this case, all of it was kind of relevant. But in the actual applications you'll be looking at later on, usually it's only one thing that matters, so you'll be tracking that specifically. But it doesn't hurt to have it all on the table just in case, especially as you're learning for the first time. I don't think there's anything special to talk about here. This is just another, it's a little bit special. So basically, flowcharts don't always have to go straight down and to the right. You can actually have things go back in on themselves. Like for instance, you're taking some n value in. If n is greater than or equal to 3, it goes to the right. You subtract 3 from it, and then you shove it back into this question mark. So basically, if n was like 1,000, right, you'd be going through this loop several times over and over again. And then eventually it won't be greater than 3, in which case you'll print n. Does this actually do... Yeah, it's just there to find the remainder. So, the actual purpose of this is sort of whatever. I just wanted to highlight that you don't have to go all the way down always. Some algorithms will go back on themselves when multiple things have to be done over and over. This was here to try and find the remainder after a division, which, fun fact, can be done with repeated subtraction. Because, you think about how many ways can, 3 fit into, I don't know, 15. You'll just keep counting up 3s until you can't fit 3 in there anymore. That's what this is doing, but just sort of doing it from the reverse. It's going backwards instead of going forwards. But okay, cool. So that's it for the fundamentals there. Before we get into some of these questions, is there anything I should clarify? Cool. Okay. These are sort of whatever. We're just sort of seeing the basics of assigning a variable to a value or vice versa. Probably this will get us a good understanding of... we won't have to usually complete our own flowchart, but being able to write your own flowchart is definitely indicative of you understanding what's going on. So let's give that a shot. Part of the challenge is going to be using the right shapes and the right sort of language. So we'll keep referring back to the book to get that right. Just a question. I joined late. What actually is this concept? Don't remember A1, A2. Yeah. So this is a relatively new concept in methods, algorithms, and pseudocode. So this is all the way at the bottom of your Cambridge Unit 1 and 2 book, if you are in Unit 1 and 2. I see you joined up a joke name, so I don't actually know who I'm talking to. So whichever one you're in, Unit 1 or 2 book is where this is, and it's something that does show up in the final exam as like anywhere from like 2 to 4 marks. Yeah, no, you're good, mate. It's fine. But okay, so we're just going to do question 3 here. So we're going to try and do a flowchart for it specifically. How do we start all flowcharts? While you have a think, I'll write out the piecewise. Okay. So I've got the relevant information down on the screen share, on the handwritten notes bit. I've also pulled up, here we go. Here's the example that's going to be very close to what we have to do. Let's see if we can modify things to match what we need it to do. So if you have a look back at the screen share, how do these things start?
We have to use the diamond, or was it the oval?
Yeah, so we would use this oval to start it off. All of our algorithms, pseudocode, these flowcharts have to start with these start buttons and end with the end button, which again is fully highlighted in black for some reason. So yeah, we're going to write it up start. And then yeah, you alluded to it as well, which is the actual like, first point of doing something new would be these sort of diamond looking things. Oh, I guess parallelogram, however. Cool. So as far as us implementing this, do we have to change anything from what's in there?
We can add a conditional at a diamond.
Yep.
Look for x's less than 1.
For x less than 1, yeah. We probably wouldn't put that in right away, though, because we haven't got input in from x yet. So x is still an input in our system. There's only one variable there, so you want to put that one in first. But yeah, you're right. When we do get to that decision diamond, because our breakpoint is at x greater than 1 or less than or equal to 1, then yeah, we would be doing that addition. So let's just get there. So we got input x, and then for our diamond would be, you could actually do it a couple of different ways. How did you want to write this statement? If x is,
I usually write if x, then the conditional.
yeah,
So it is x less than 1.
yeah, we could do x less than 1, sure. Because you got you could write this one, you could write that one, you could write your own one. There's a lot of different ways you could do it. Just a quick thing, I have seen that question come through. I feel like that'll be something I'll ask at the, I'll answer at the end. We'll keep on topic for now, but I'll definitely answer that. But cool, okay. So is x less than 1, and then what do we do with those? So we got this decision diamond now.
We can add paths to it if it's true, or actually we can modify. Can we modify the conditional to include x less than or equal to 1?
Yeah, we can do that. X less than or equal to 1.
Yeah, and then line coming out of it saying if it's true or if it's not true.
Yep. You can use true false. That's very programmer. You can say yes no. That's what they're using in the book, but both is perfectly fine. Doesn't matter which way you do them, by the way, whether you do true on the left, false on the right, as long as you actually write the right thing afterwards is what really mattered. Let's think about the true path here. So it would go in the true section.
If it's true, it will use the function 3 minus 2x.
Yep, 3 minus 2x is going to be there. So 3 minus 2x is going to go there. Is that all that goes there?
Yeah.
So just a statement 3 minus 2x isn't actually a thing that an algorithm will do. We have to make sure we're either taking input from things, assigning variables, calculating variables, or printing. This is none of those things just yet. How do we slightly modify that to make it an actual statement? And you can refer to the screen share if you need to.
We use the arrows.
Yeah, correct. By default, just because we're in methods, we'll typically assign it to y, because we usually think of y as the output, but technically speaking, you can use whatever one you want there. All that matters is what you'll end up doing at the end when you print it. But okay, so if that's the true one, then this will be the false one, which means we're going to be using the 2x plus 3, because again, it's got this conditional of x being greater than 1, right? If x is less than or equal to 1, we go down this path. If it's not, we'll go down this path. So 2x plus 3. Cool. Both of those are going to converge onto some statement. Yeah, what's it going to end up saying at the very end? Well, the last two things anyway.
We do a print statement.
Yep, print statement.
For y.
That's it. If you used a different letter in your own flowchart, then just make sure you print that letter. So, if I said print Z for whatever reason, then, all these would be Zs. Print Y. Try to get it looking diamond-like. Again, you won't be writing these full flow charts yourself, but it's good to think about. And that is a picture of my dog. Why? Okay. That's kind of creepy, but sure. And then we finish with an end statement. It's going to have the exact same thing there. Does anyone know who that is? Very strange. Anyway, that's one simple algorithm there. We've slightly modified it to accommodate the new piecewise. I don't feel like we need to go through too many of those kinds of examples, but if we do, feel free to let me know, because it's only we're gonna add on to it with additional topics still. So if we still need to clarify some of these things, happy to do so. Any preferences? Should I keep going on? Yes, Taihan it is. I don't know who that guy is, but yeah, very strange. I'm probably just going to ban him. Cool. Anyway, if there's no further questions, iteration and selection. So this is getting more into how we can loop back on our programs. So instead of just going straight down, you might want to do a sequence of things multiple times over and over again. In this example here, we can see that we have some interest thing that we're trying to calculate. We're trying to calculate the value of the investment at the end of the year for the first 5 years based on these initial things. Hang on, another question. Are these algo questions common in SACs and final exams? Yeah, so I was saying at the start of the lesson, this, for SACs, again, I can't say too much. They should be testing this stuff. For the exam, it'll be something like 4 marks on your tech active. It'll be, I think, 1 or 2 multis, and it shows up like at one spot in the extended response. A lot of types of questions will be, they'll give you the full algorithm. They might ask you, what does it do? Or what's the final outcome? Or they'll basically remove a blank, tell you what it's supposed to do, and then you have to fill in that blank. They're, relatively small contribution as far as marks are concerned, but that can technically be said about all the topics, right? Like if you do a circular functions question, perhaps, which has been a topic recently, sketching it will maybe show up once in the entire exam for tech 3, and that'll be worth maybe 3 to 4, 5 marks. So the relative contribution is actually similar to the other topics that you look at. It's just that this one is so far removed from what we typically think of as method stuff. But it is there, and it is just as important as the other topics. Okay, so the difference between this kind of approach to iterating on things over and over again is that we add additional variables that aren't necessarily immediately obvious to us. Like we're having this A being 100,000, which is going to represent our initial investment, and then n being assigned to 0. If you don't have some initial reason to have that variable immediately or something to assign it to, you'll just default to assigning it to 0. It's good practice, and you'll see that for a lot of algorithms, they'll assign all possible variables that will be used, will be done at the very start of the flow code, or the flow chart, or the algorithm. And then yeah, so the next stage here is going to be applying the interest. So the interest is 5%, so you're going to have 1.05 times the amount, and it's just replacing our initial value. So basically, A is going to get 1.05 times whatever it was initially. But then it's also going to do n gets n plus 1. It's not immediately obvious, unless you read what they're saying about what n actually does here until you think about what the overall goal is. We're going to do this for the first 5 years. N in this case is going to be tracking essentially the number of years of interest that are applied to it. So n being n plus 1, we started at year 0 with this initial value. We've applied this set of interest, and we're incrementing the number of years that have gone by. From there, print n, print a. So essentially, why do we need this? Technically, that isn't required right there. This question has only really asked us to find... Oh, no, at the end of each year. So it is required there. I thought it was only going to be at the end of the first 5 years. So, it's a minor nuance to think about. Do you need to print it every single time, or do you need to just print it at the end? If you need to print it at the end of every single time, then you want to have it inside of your loop. The colors are a bit weird here, but that print statement is in the loop. Versus if you had it on the outside, then you'd only be printing it once at the very end. But yeah, we're printing the year and the money that was earned in total over the duration. If n is less than 5, we would continue going back through that loop. If it's not, we finally end. So now n being less than 5 should make a decent amount of sense, given that we want to do it for the first 5 years. So n will count from 0 to 5, essentially, because every time we go back to here, we're incrementing n and we're applying interest over and over again. And these kinds of breakpoints here, whether you include n equals 5 or whether you exclude n equals 5, every person who ever does programming ever will come across this and be like, shit, do I make it inclusive or exclusive? That's where this sort of thing can help. Literally just bash out the numbers yourself and then see, okay, did I print it enough times? If you did, then call it off as soon as you printed it enough times. Even to this day, I have a background in programming, by the way, and to this day, I still just sort of I just run it with one guess, and then if it works out, it works out. If not, I make it go one further or one behind, whatever it needs to do. And this is just something you can do in your CAS, right? You literally just, write what you think it should be, CAS it out 5 times, see what happens. Clear enough the use of additional variables to help us keep track of where things are? Okay. Sequences, what's this? I think that's just describing what's going on there. Let's have a look. Is this example anything new? Consider the sequence. Oh, sure. Okay. This is more a special thing, really, where you're just checking sequences of numbers. So basically, the n is not necessarily like a variable. It's the number of times you want to iterate over it. So like if n was 5, you would do f of 1 and then add f of 2, 3, 4, 5, and so on and so forth. I don't think there's anything really much else to talk about there. It's just another way of compounding values onto themselves. Maybe the thing of use to talk about there would be the fact that we're using we're using actual function notation here. So basically, anything that is defined in the actual question statement itself, like as a function, you can just write the function, right? So if you have f of n is this, then you can literally use f of n, so long as n is actually defined as a specific number. So that can help truncate the amount of effort and writing you're putting into these things. But otherwise, this isn't really that much different to the other thing. You're still looping a certain number of times, and you're still just sort of repeatedly adding to or multiplying into some value. This is just another version of a piecewise. They don't have to be using the inequalities, could just be evens and odds, in which case your decision time would be, is it even? But otherwise, this is still not that much different. That should be about it for all. Oh, maybe there's an else if. Oh, they're not even going to show a. This would have been a good example to have a look at, but they didn't actually write the diagram for it. Basically, what happens if you have more than one stage, or I guess one decision to make. Basically what you would be doing is you would be writing these back to back on each other. So you've got this sequence of possibilities, right? So if A is less than or equal to that, if it's between these, if it's between these, if it's between these, basically every yes would feed into its own outcome. So yes would feed into 0, yes would feed into that, yes would feed into that. But every no feeds into the next decision diamond. So if I were to draw a rough idea of what that looks like on the handwritten bit, we've got, I'm just going to make some simple numbers. So, you know, A less than 1, I'm not even going to draw the diamonds because it's challenging. In the no, that would feed into, I don't know, A between 1 and 2. If no, that could feed into the 2 and 3. And all the while with the yeses, those would all feed into whatever that function was. So let's say if a was less than 1, the function was y equals x plus 1. Maybe this one is, sorry, it wouldn't be equals, it'd be arrow. Y gets that. X plus 2. Y gets x plus 3. So basically every time you don't hit one of the things, you move on to the next one, so on and so forth until you get to the end. Then typically all of these would sort of combine into each other for a final print at the very end to, well, to do exactly that, print Y. They all use Y, so you can, yeah, combine those all in. Okay, let's have a look. Is there any good questions to have a look at for here? Illustrate the algorithm, demonstrate the algorithm. Yeah, okay. This is, so they've described what they want to have in the algorithm for question 1A. But it's not, the first 2 steps are going to be fairly obvious how you write those out. The third step is going to be a bit more broad, and it's going to require a bit more more to it than just a single thing there. So let's start writing that one out. So we start all algorithms with a start button. So let's get that sorted. Then the very next thing. So step 1 says A gets 10 and N gets 1. Not a whole lot to talk about there. I'll yeah, how should we write that one out? Or at least what would we encapsulate that in? Like what kind of shape should go over that?
Is it the parallelogram?
Parallelogram. Okay. So worth really discussing here the difference between when you would use a parallelogram or when you would use a regular rectangle. So parallelograms are there for when you're taking things in from elsewhere and you don't know where you're starting. The nuance here is that our algorithm is actually setting these variables itself. If we have a look at the question, it says get a equals 10 and get n to equal 1. It doesn't say the algorithm initially takes in an input. The implication in this wording specifically would tell me that it's actually what you would refer to as hard-coded in the real world. You would say these variables are what they are right now at runtime, at the start of the algorithm. You're not actually taking that in from elsewhere. A little bit of a nuance there. So you use the parallelograms when you're taking things from outside or pushing them to the outside, and you would use the just regular rectangles for if it's a process step, right? It's something that the algorithm does every single time, no matter what. If it asked us to generalize it for all a and n, then yeah, we would just use that as an input instead for parallelogram. But cool, okay. Next up is the exact same thing, right? It's just assigning values, so nothing really new to talk about there. I don't know if I said this tip already, but if for whatever reason you are having to write your own flowcharts, best to write the thing you're doing first and then draw the box over it later. Because if you draw the box, you might find very quickly you don't get enough, you don't have enough space to write what you want to write. So this is a gets a plus 5, and this is going to be n gets n plus 1. Cool. Now for the tougher bit. Step 3 says repeat step 2 while n is less than or equal to 5. There is no one thing that'll do that. So if you do suggest things, a lot of the things you'll have to worry about here would be iterating on your algorithm. You'll write some initial statement about how you think it's going to work, and then realize pretty quickly you have to do something else, or vice versa, right? So we want to repeat this step 2 that we just wrote over and over again while n is less than or equal to 5. Any ideas how we could start getting that to work?
We can add a diamond the decision thing.
Yep.
And we can check for if n is less than or equal to 5.
Yep. Sounds good to me. Decision diamond. We'll have a... Actually, this will be an important decision. Where would we, just for the sake of neatness, what should the true falses go to?
The true should go to step 2, and if it's the if it's false, it just ends.
If it's false, it just ends. Yeah. Yeah, I think ending is appropriate there. I thought we might maybe put a print statement, but I guess it doesn't actually tell us to print anything, does it? It just kind of says, do that and then end. So I guess we would just end. Nice. Now to test it. So, one of the things that can get a bit weird is that we've already assigned n as 1 here. That's significantly different to n being assigned as 0, because if n is assigned as 1, then the first time you do this, you're going to now have n as 2 for this thing. So n is no longer keeping track of the number of times you've looped this. It's 1 more than the number of times you've looped it. Now, I don't think that's going to matter here specifically, because it literally just this program doesn't do anything. It's not like designed to do much. It's just saying, hey, step 3 just wants to repeat step 2 while n is less than or equal to 5. And so, did he just rejoin again? Okay. Cool. He's banned. Yeah, so what was I even saying? Yeah, this algorithm doesn't it's not trying to duplicate numbers, it's not trying to calculate interest, it's just kind of there to demonstrate things. But these are the kinds of things you might think about when debugging, hey, does the thing do what I think it does? That's all I wanted to highlight there. Cool. Okay. Is there anything else worth discussing here? some of the sequence. Yeah, I can't imagine too much more to have a look at there. We're coming up on time, so it's probably worth looking at the final section chapter here, which will be the actual code stuff itself. So how you write it in a more programming type language. Because I know a lot of you doing methods want to get into STEM related things because it is a prerequisite for that. And so pretty much any STEM thing that you get into, you're going to have to be at least somewhat proficient in code, which is kind of why they've got this in methods now. But okay, so this section is going to start graduating away from using flowcharts to now using code statements. This is, as far as you're concerned, basically the exact same thing. Code flows from top down to bottom. The only thing that's going to be a bit different is when it loops, there's not going to be like arrows pointing to where it goes. They're just kind of going to kind of be these self-contained things. But okay, so if then, this is essentially just your decision diamond. If this is true, do that. If it's not true, do that. So that's just a direct replacement for the decision diamond. The conditional goes here. The thing that it would flow to would go there. They work the exact same way. So even though code does flow from top to bottom, this one, as soon as the first condition is met, it goes straight to the end, wherever the end if statement is. I've seen a question, just wondering what coding languages do you know or have used? Nice. So I've used a bunch of them. So we'll go C++, basic C. I've done a bit of Python for one of the, what was it? Python was for a microprocessor thing that I had, basically just a little device that you could program. I've used assembly, which is a step underneath in a step more specific than what we're looking at here. Like this is an if statement. It's very high level. It's just if this, do that. Assembly code is when you go down to the individual instructions that are run on the actual chip itself. So an if statement, yeah, how would you even start describing that? We're going to get a bit high level. Then basically, assembly sort of goes a step further and breaks this if statement up into like 3 or 4 separate things that have to happen to execute an actual if statement on a real computer. Way beyond the scope of this, though, so I won't go too into detail of that. And the other last thing would be hardware description languages. So that's where you're literally coding in actual logic gates. So your computer is made up of a bunch of different logic gates in there, and there are certain devices called FPGAs that you can program the actual physical chip on. So it's pretty cool. Cool. Okay, anyway. So if statements, that's just a replacement for decision diamonds. As for how they look in code stuff, you're not using blocks anymore. You're now just writing top to bottom and using these little indents as well to sort of make things neater. You don't technically need them. Code, even in the real world, will run if you don't have indents, unless actually, I think Python needs its indents. There's so many different little nuances around it. Basically, as far as you guys are going to be concerned, indents are there to make life a lot easier, so you can see, hey, this thing only runs in this little section and nothing else. This one's a very basic, kind of like the what was it? The piecewise function, right? If we have something greater than or equal to, we do this, or we do that. These can be extended even further. So our decision diamonds were kind of limited to like 2, maybe 3 choices because just physically on the, you could just write more decision diamonds, but basically any one given decision diamond really only has 3 additional branches it can have. With if statements, because you're now writing in code, basically what you do is for every individual or extra condition that you want to add, you write else if there instead. And again, these run from top to bottom. The first one, the condition is met, is where the entire algorithm, that entire if statement stack will end. So basically, let's say the mark was 80, right? If mark greater than or equal to 90, well, okay, we're not going to do that. But but it is greater than or equal to 75. So this algorithm would print B, ignore everything else here, and then whatever's written immediately after the end if is where we continue on from there. Okay. For loops. So this is, again, sort of decision diamond-y type stuff, but it's when your decision diamond goes like back up to an additional or a thing beforehand. For loops will loop for a number of times described by this statement here. So basically what you have is a variable that will keep track of the number of times you have looped. Typically you'll use I for like iterations. And then this describes how many times it's going to loop from some start point to some end point. So basically if we have a look at this one here, I is going to start out with the value of 1 and eventually end at the value of 4. How does it get there? Well, basically, every time you hit this end 4, when you go from top to bottom, I will get incremented and you'll go back up to the top here and run the next line. So is there any more that have, yeah, here we go. Here's one that's, it's a while loop, but it's got, let's just pretend this says if. Basically, I wanted to show what happens if there's more than one line of code there. So you'll have your iterative statement here. You'll do line 1, you'll do line 2, you'll hit this end, go back up, increment the value, do this again, do that again, here. Go back up, increment the value, down, down, and you keep doing that until you hit your end. So for the first loop, I would be 1, then it will go to 2, you do it again. Go to 3, do it again. Go to 4, do it again. It now hits 5, that is outside of the boundary, and then you print. That's the bit that I'm going to have to clarify actually. Does it ever actually hit 5? No. It's going to end at 4, and it's not actually going to jump back up. There may or may not be some actual programming language that would increment it up. I think in most it's going to end at 4, and that's going to be the case here as well. It's going to actually end at 4. So when you hit 4, you do it, and you don't actually jump back up anymore. You don't increment. You just continue on. As for what it's doing, there's nothing like, it's just sort of doing some basic whatever addition. So if I was 1, I squared is now 1. When it goes to 2, 2 squared is 4. So on and so forth. That part's not too important. What's more important is the structure here. Oh yeah, I've seen your questions, Ihan. I'll probably just answer that at the end. Yeah. Okay. That's just another loop for... Oh, actually, this one's a little bit different. You don't have to have predefined... Sorry, there's actually 2 things I want to talk about for this. What you'll notice is, in this case, the variable is actually defined in the for loop itself. I mentioned earlier that it's good practice to define all of your variables at the very beginning, either using inputs or assigning them to 0, like they have here. Any variables for loops, as far as method is concerned for pseudocode, doesn't need to be defined before use. You can actually declare it in here specifically, and the reason why is because it's, you're setting the range of where it's going to start and where it's going to end in that statement itself. The other thing that's different about this is you don't actually have to have numbers for your start and end. As long as both letters are defined as a thing before use, you can put letters in these spots as well. So for instance, n came from somewhere, so we don't know what n is going to be. In this case, they're telling you set n equals 5. So essentially, this would now say I would iterate from 1 to 5. Otherwise, yeah, basic thing to discuss there was you can use letters there instead of numbers as long as those letters are actually defined as something, or will be defined when it starts. So that's one we've basically already done as far as our flowcharts. That is a replacement of our decision diamond that goes backwards on itself. This next one will be a little bit different, so I guess before that, is there anything here that needs to be clarified? Okay. While loops are very similar. They loop, so basically you have a start and an end to the loop. However, they don't have a predefined end to them. For loops will always run for the same number of loops every single time, as long as what's coming in is the same, 1 to n. As long as n is always 5, then it'll always run 5 times. While loops have a condition for which they should break, rather than a set or predefined number of loops that it should take. So just for anyone who is interested in code-related stuff, you would typically use a for loop when you know you want to do it a certain number of times. You would use a while loop when you don't actually know how long an operation is going to take. Like in this case, they use division here. If you knew how long, or if you knew how many times you would need to do 72 divided by 14 ahead of time, you wouldn't need the algorithm anymore. You would just, know your answer. And so because we don't know how many times it's going to take, we're just going to set a condition on when we're going to break the loop rather than tell it to loop X number of times, 4 number of times, 5 number of times, whatever. Otherwise, it all works the exact same. So we have our couple of variables, count and remainder. We saw something like this earlier, which was repeated subtraction can be used to do divisions. You're just counting basically the number of times you fit 14 into 72. And because we don't know how many times it fits, we're going to say, hey, I'm going to continue so long as the remainder variable is greater than or equal to 14. If we see here over and over again, it'll take 4 loops to get it to 16. On the 5th loop, it'll be 2. And so on that 5th loop, when you've done this bit here, you would get to 2. It would come back up here. It'll say, cool, 2 is not greater than or equal to 14 anymore. End while, and then do the next statement right after. Print. That's how a while loop works. Just a condition for ending rather than a predefined number of loops. Just going to quickly check to see if there's anything else. Yeah, not too much else. This is just saying you can nest loops into each other. So this is where having indents is really important. So, you've got this big red one where everything inside the red will loop twice over. And then you've got this other one inside of it that's in the orange. Everything in there will loop 3 times. So, more complex things can have nested loops, which you typically don't want in real code if you can avoid it. But they do it in there just because. And maybe the last thing, just before we run out of time, would be very quickly how you define functions. We saw earlier that at the top of your information, like the actual, question background, you'll have like f of x is whatever. In actual code, you can write it using define statements like you would on the CAS. In fact, the syntax is almost identical. You define your f of x or whatever you want to call it. Only difference is you also then write the variable which you're assigning the rule rather than just the function. And then return. So return is similar to, as far as you guys are going to be concerned, return is basically the same as print. It's the final thing that the algorithm does to say that it's concluded, and then it returns back to wherever it came from. Cool. That's about it for actual content there. I'm not going to have time to practice any of them, but if you guys want to, it is right at the bottom of your book, basically, exercise A3. Same with the other ones, right? It'll be something where you'll actually see most of this stuff in Unit 1 and 2, or even Unit 3, 4, will be interspersed into the other topics. Like, for instance, we did bisection method not too long ago, and if I can find it real quick, pretty sure they showed some pseudocode in there. Yeah, there you go. So basically, where applicable, they will start describing things in terms of algorithms pseudocode. Usually it'll be these iterative things, right? If you're in a bisection method, it was you had an upper bound and a lower bound, and you kept doing it over and over and over again until you felt like stopping, basically. that's where they'll typically write algorithms for it, get you to debug them or however. But yeah, it's a small portion of what you'll actually be doing in the actual exam, but like proportionally speaking, so is everything else, right? There's so many topics and methods that they can only really show a certain portion of it anyway. So roughly speaking, most things, including pseudocode, have the same relative proportion. That's about it for the lesson here. We've hit time. I'm just going to stick around and answer a few questions that I've got to. And yeah, if you guys have any further questions, feel free to stick around or even message me after class. That's fine. First question, wondering how related methods is to financial and economics related stuff. I use some mathematical methods stuff for literally my own finances. So, one of the things I do for this business specifically is track ad spend relative to return on investment, basically. Because I run ads to get you guys into these classes, I need to make sure I'm not going to go broke by doing it. And so what I'll do is, in fact, I did it on my CAS, which I cleared, and I can't actually show. But basically, I literally used my CAS, just basic define statements, to essentially implement a bit of a compounding interest thing, and just sort of seeing, okay, what happens if I am, staying at this level of ad spend? What if I increase ad spend over time? And you just sort of model these things over time. And so, yeah, basically, essentially, you can use methods to help with this sort of stuff a lot. Excel, right? Excel, especially this, what we just discussed right now, pseudocode. Excel can be considered a programming language, right? You've got the if statements, you've got like your VLOOKUP, your XLOOKUP. I don't know how much Excel you guys have done. Google Sheets, same thing. Knowing how to use programs, knowing basically the inputs to those programs, the outputs to those programs. I think methods, all the STEM related stuff is going to help with your financial and economics stuff. And yeah, all of you guys came from ads, definitely. So yeah. Cool. I guess maybe just to cap off, if any of you guys show up with a weird name, I'm probably just going to ban you because I think it's the guy who's, I'm assuming, crashing these. I don't actually know who that is. So stick to the names you're already using. I know no one's going to change it, but if that's a regular thing, I'm just going to consistently keep banning that guy. And also, if anyone knows who that is, feel free to let me know. I don't know how they would have found the link or a picture of my dog, oddly enough. Like, is anything of mine public now? I'm curious. Because that photo, where does that photo come from? That's on my old phone. That's the phone that I'm using as a camera right now to aim at my the handwritten notes thing. That's on that, and this thing doesn't have a SIM card. So God knows where he got that from. Anyway, just a weird thing. He was here last week too, as well, same time, under a different name. Anyway, cool. I'll if there's any further questions, I'll answer them here. Otherwise, I'll leave you to enjoy the rest of your day.
Thanks.
No worries.
Have a good day.
Cheers, mate. You too.
Thanks, Chris.
Yeah, no worries. Take care.